recursion is one of those topics in data structures and algorithms that throws people off for a loop. And I wanted to talk about it today because it can be a little bit difficult for people to grasp. And I know it was difficult for me to grasp. But we'll use the Fibonacci sequence, and I know this is a tried and true example, so you may have seen this before, but I do think it is good to showcase what recursion is all about. So for those who don't know, the Fibonacci sequence starts off with two numbers, 1 and 1. So it's a series of numbers, one after the other. And we calculate the next number in the sequence based on the previous two numbers. So we just add them together. So 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, 13 plus 8 is 21, and then from there it just goes on and on and on. All right, and so here we just basically start off with two numbers, and then we grow our list from there, and it goes, you know, up to infinity, however high you want it to be. All right, so we can program the computer to generate the Fibonacci sequence. All right, and so what I want you to kind of do is think about this series of numbers kind of like an array, where the first number is at index 0. I'll use different colors here. So if you fix this at index 0, this is index 1, 2, 3, etc. All right, so you can think of this like an array of numbers. All right, each number being at a certain index. Now, we know basically what we want to be able to do is we want to be able to give an index and say, okay, at this index, what number would be there, right? So if I could give my Fibonacci magical function the index of 3, it should spit out 3. If I give it 4, it should spit out 5, okay? So I want to give it an index that tells me what number is in that part of the Fibonacci sequence. Now here's how we can think about recursion. This is where recursion comes in. So I think we got the point here, so let me kind of get rid of this. And then we'll start going from there. All right, so what we can think about is that we have a basically what recursion does, and what you'll hear most people say, is a recursive function is a function that calls itself. All right, so a function that calls itself. And that's all well and good, but like, what does that actually mean, Jonathan? What it basically means, so let's take this Fibonacci sequence, for example. All right, so I want to get, let's say, f of 5. All right, so I'm using function notation. So if you're completely new to function notation, what I'm saying here is I have a function. Let's call it the Fibonacci function. Its input is 5. I want to get out output a certain number based on the Fibonacci sequence. What number would go at space 5 in the Fibonacci sequence? Okay, well, there is a pattern here, right? Because we know that the Fibonacci is equal to the sum of the previous two numbers. But Jonathan, we don't know those numbers. I have no idea what the previous numbers are. I just know f of 5, and we're trying to calculate that. Well, let's think about it, right? Because we would know that this would be f of 4 plus f of 3. All right, f of 4 is the number before f of 5, and f of 3 is the number before that. So if I take these two numbers and add them together, then I should be able to get f of 5. Okay, here's where recursion comes in. Recursion is basically kind of like a chain, because if you think about it, we don't know 5. Okay, we can break 5 down into f of 4 and f of 3. But then you're like, well, wait a second. We don't know f of 4 and f of 3, so we can break those down even further. All right, so it might look something like this overall. The way I like to look at recursion is kind of like a pyramid. All right, at the top is what we're looking for. We're looking for f of 5. I want to find the Fibonacci number at index 5. Well, we can break that down by looking at f of 4 and f of 3, right? But we don't know those. I have no idea what those are. We could break those down into f of 3, f of 2, respectively. See where this is going? F of 2, and then f of 1, because those are the previous ones. And then you could break this down, f of 2, f of 1. This one's just f of 1, and f of 0. And so on and so forth. So you can think of recursion kind of like a pyramid. So essentially what recursion means is, hey, I have a function, right, but I don't know this number. I need to call the same function to calculate something else. It's handing off the work, right, f of 5 To calculate f of 5, you need f of 4 and f of 3. So f of 5 is saying, hey, I can't do this work by myself. I'm going to hand off some of the work to f of 4 and some of the work to f of 3. Then the f of 3 and f of 4, we don't know what those are either. Well, Jonathan, won't this just go on forever? Well, not quite, because we actually do know, at some point, we do know what are called base cases. All right, so what are the base cases? Let's look at f of 2, right? F of 2 is equal to f of 0 plus f of 1. Well, if we look at the Fibonacci sequence, we kind of just said that the first two numbers in the Fibonacci sequence, right? So I'll just do a little bit of the Fibonacci sequence. We said the first two numbers in the Fibonacci sequence were 1 and 1, right here. We declare that by fiat. We just said that when we defined the sequence, we said the first two numbers were 1. Like, that's it. And so because we defined that, these are our base cases. Base case. And the way I remember base case means it's at the bottom of the pyramid. All right? So if we draw this pyramid out with all of our different function calls, you're going to find the base cases at the bottom of the pyramid. Okay? F of 0 and f of 1, I actually do know what those are equal to. F of 0 is 1, and f of 1 is 1. All right? So I do know what these two functions here, okay, I'm going to just put a little square around them. I do know what these functions return. And so what I can do is, okay, great. I can add these together, kick it on up to f of 2. Well, f of 2, now I know what f of 2 is. It's 1 plus 1, 2. Okay, this is going to be 2. So you see how handing off the base cases are actually they're really the part of the recursive tree that's doing the work. They're like, basically they're like the lowest grunt workers, right? So like you have management, you have middle management, and then you have the people who are on the front lines, who are like in the store, at the cashier, stocking the shelves, checking out customers. Those are the people who are actually doing the work of the store. Without them, everything crumbles, right? So the base cases, right, are at the very bottom of the pyramid. We know those. I know what f of 1 and f of 0 is, all right? So overall, once we have the base cases, they do their job. They say, okay, cool, f of 1 is 1, f of 0 is 0, add them together, you get 2. Great. And so now, we should be able to figure this out, right? Because f of 2 is 2, we know that. F of 1 is 1, so therefore f of 3 is 3. Then we get 5. See how it bubbles up? Okay, so once we figure out the bottom part, it kicks it back up to the previous layer, which kicks it back up to the previous layer, which kicks it back up to the previous layer. All right, so there we go. We get f of 3 is here, and then we get 8. All right, so 0, 1, 2, 3, 4, 5, right? So we get f of 5, which is 8. Now, here's the thing. This is very difficult usually in people's minds to kind of wrap their head around because there's so much stuff going on, right? It's hard to, it's very easy to draw this out, but it's very hard when you're programming to think about this. So what I like to do is kind of follow a template, all right, in order to write recursive functions. So like, this is all well and good, understanding it's a pyramid, understanding what a base case is, but we need to like code this. And when you code it, you actually kind of just follow a basic pattern. And that's kind of the cool thing about recursive functions, that when you actually code them, they're pretty easy to understand. So hopefully this made sense, all right? Remember, the whole point is that we're starting at the top of the pyramid, which is the question that we want to answer. What is f of 5? We break that down into its parts. F of 5 could be answered if you do f of 4 and f of 3. Okay, f of 4 could be answered if you do f of 3 and f of 2. Okay, and then you keep going until you reach the base case. The base cases are actually where you just know what they are. F of 0 is 1. F of 1 is 1. That's because the first two numbers in the Fibonacci sequence are 1. So I do know what f of 1 and f of 0 are. If I know what f of 1 and f of 0 are, then I know what f of 2 is. If I know what f of 2 is and f of 1, then I know f of 3. If I know f of 3 and f of 2, I know f of 4. Then f of 5. It bubbles all the way up back of the period. So you could think like it goes down the pyramid first till it reaches the base case, then it bubbles back up. And then you'll have your answer once you reach f of 5. So let's do the like naive coding. We're gonna basically do the basic algorithm. Then I'll talk a little bit more how to make it optimized. But hopefully this helped to clear up how recursion works. All right, let's actually write out our recursive function. And one of the cool things about recursion is that when you write the code, it's actually very short and simple. I know that the explanation probably made your head explode, but when we actually write the code, it's actually like 4 lines or something like that. Like it's very, very direct. All right, now, the first thing we're going to run into a problem is that when we have a recursive function, obviously the function is going to call itself. All right, so for example, let's say I have recursive fib like this. This is going to be a problem, mainly because we're going to have a maximum recursion depth exceeded. What that basically means is that the function called itself, which calls itself over and over and over again ad infinitum, okay, forever. Well, the computer is not infinite, so the computer is like, listen, I can't do anymore, right? We're in an infinite loop. I'm just going to stop, and you need to go fix this. All right, so we're in an infinite loop, and so one of the problems with recursive functions is that we could enter into an infinite loop where the function just calls itself forever. So what do? All right, remember back to our example. Recursion is kind of like a pyramid. We have the topmost layer where it's the work that we want to do, our goal. Okay, f of 5, and we hand off our work to smaller problems. F of 5 is f of 4 plus f of 3. Those, we could sort of simplify it to those smaller subproblems. And we go down and down the pyramid until we have an actual problem that we can solve without having to ask other problems what their solution is. So for example, I already know, for example, f of 0 is going to be 1 and f of 1 is going to be 1 because that's what we said. Like when we first started this, like we said that the first 2 numbers of the Fibonacci sequence are going to be 1. All right, we waved our hand and said that's what's going to be. That's our base case. So usually you write your base case to stop the recursion. Okay, it stops the recursive function from calling itself any further. And it's very important that you have your base case because otherwise it goes on forever. So what's our base case? If a number is less than or equal to 1, then return 1 in this case. All right, so basically these are the 2 base cases, and these are the 2 problems from the outset. I know how to solve them. I don't need to break the problem down any further. It's in the simplest form it can be. So go ahead and solve it. Now, for the next part, it's for a problem where I don't know what the answer is automatically. So for example, f of 2. So here, right here, it's the sum of the previous 2 numbers. Let's say this is 2, right? So it's going to be 2 minus 1, which is 1, and 2 minus 2, which is 0. So add these 2 numbers up to get this one. If I have 3, I have to add these 2 numbers up to get that number. All right, so I'm calling the function, okay, with the previous 2 indices. So I'm going to take the recursive fib at num minus 1 plus recursive fib at num minus 2. Okay, get the previous number and add it to the number previous to that. All right, so this part is a problem I can't solve without breaking it down into smaller problems. This part is a number I can solve by breaking it down into smaller problems. All right, now this is not the most optimized solution, but it works. So let's go ahead and try it. All right, we get 13. Awesome. All right, so 0, 1, 2, 3, 4, 5, 6 is 13. If I decide to do next one up, let's go, I don't know, some more higher. All right, let's go do that. All right, looking pretty good. We're getting the right numbers. Everything works great. Now, what happens when we get to like something larger? All right, let's do 999. We're waiting. We're waiting. We're waiting. It's taking a long time. Let's take a break and let's see how long it takes. As you can see, the computer's just kind of hanging, but as you can see, the program's still running. It's just taking a load of time, okay, to figure this out. And we don't have time for this, all right? So let's see if we can optimize this. This is, again, I told you this was not the optimal version of figuring this out. In fact, you wouldn't even use recursion to figure out the optimal version. Surprise, surprise. But we're going to try to make this better, all right? And we're going to talk about, we're going to look back at our tree, our recursion tree, and let's see if we're kind of being redundant. Are we doing work that we've already done? Because one of the things you don't want to do in programming is if you've already done the work, you don't want to do it a second time. That's a really core fundamental of programming. Let's see if we can apply that to recursion. Hi, my name is Jonathan Hopp, and if you're enjoying this tutorial, I invite you to visit my website, codingyourcareer.com. I've got courses on Java, JavaScript, TypeScript, and all of the famous frameworks like React and Angular, the kind of things you'll need in order to break into the world of tech and get the knowledge that you need. It's even great for people who are already in tech and want to level up their skills. So it's codingyourcareer.com. Let's continue with the tutorial. All right, now we did the naive implementation, but we could make our recursive function a lot more efficient. All right, so what do I mean by that? Well, if we look at our pyramid, you might notice that we have a lot of the same thing going on. What do I mean by that? Okay, let's say, for example, remember, we're going to go all the way down the pyramid, we go to our base cases. I know what f of 0 is, and I know what f of 1 is. So I'm down here, all right? And so great, I use f of 1 and f of 0 to calculate f of 2. So I know what the first two numbers of the sequence are, and so therefore I add them together to get 2. Okay, great. And then I add them, I know f of 1 and f of 2, and so now I get to 3. Awesome. Now, I've done the right side okay? And so what I'm going to do is I'm going to mark off where I've done work. Okay, f of 1 and f of 0 are kind of for free. They're base cases. So since they're the case, I know what they are. But I have calculated f of 2 and I have calculated f of 3. All right, I need to calculate f of 4 now. I don't know that. Nothing from the right side of this pyramid told me specifically what f of 4 was. Okay, cool. Now we get to this part right here. And once we get to here, the main thing we have to ask ourselves is, well, wait a second. I already did f of 3, and I already did f of 2 on the other side of the pyramid, right? So on the right side, I calculated what f of 2 was. I calculated what f of 3 was. So why am I calculating them again? So if I do f of 3, I go down to f of 2 and f of 1, f of 2, but just why am I going down to this level if I already know the answer to f of 3? F of 3 is over on the other side. I could just be like, nah, bro, I don't really want to do all this stuff at the bottom. I'm just going to put 3 here, and I'm going to just go ahead and put 2 here, and skip doing all this work down here. I don't need that work. Okay, that's just tiresome. I don't want to do all that. And so therefore, now that I know what f of 3 and f of 2 are, then I can calculate f of 4, no problem, and then add these together and get f of 5, which is 8. Okay, but see how I was able to save myself some time. I already did the work on this side of the tree. Why would I repeat it on that side of the tree? Now, you may be thinking to yourself, well, Jonathan, so what, right? You save yourself some function calls, all right? You save yourself some work on this part, but you still have to do work everywhere else. And that is a fair point. However, remember, we want to scale our algorithms. If you were here for the binary search lesson, then I talked a little bit about scaling, and I'm going to talk about scaling some more so people really kind of understand this concept. But we want our algorithms to scale. Again, think about a restaurant. Certain restaurants, if they get a lot of customers all at once, I'm not talking about during the day, I'm talking about a slam. You just have a bunch of customers flooding your store. How well is that restaurant able to do what the restaurant's supposed to do, right? Restaurants are supposed to serve food, and they're supposed to, have waiters and cook the food out on time and things like that. Certain restaurants, they can handle a ton of people coming in at once. The waiters, do their job, the cooks do their job, the dishwashers do their job, everything runs smoothly, even if a large amount of people come through. And other restaurants fall to pieces, okay? Food comes out slowly, the dishes pile up, people are waiting an hour to be seated. I think everyone has had this experience at restaurants, right? Where there's some restaurants that run better and some that, well, don't. So we want our algorithm to scale well. We want it to be able to handle large amounts of input. This tree, right, the amount of work that we save may not seem like much because this tree is small. Okay, what if I kick it up to f of 1,000,000? Okay, let's do f of 1,000,000. How much redundant work do you think there would be in that tree? A ton, all right? I'm not even going to try to draw out a tree with f of 1,000,000, all right? But let's think about that. You always have to remember that when you watch videos or you're doing your own programs, you're doing them on a very small scale, okay? So even though it feels like a lot to you, the scale of a lot of programs is not huge. But once you start getting into Facebook with 100 million users, or however 2 billion users Facebook has, or whatever, right? 100 million users, 300 million users, 500 million requests. Like you have to, your algorithms are going to have to be able to handle that load. And so we have a lot of redundant work, so we need to handle that. So what we're going to do is we're going to learn a technique called memoization. All right, so let me kind of get this out of the way. All right, so it's kind of a weird like term. It's just I like to use the term memorize, but it's like memorize, but like memoize. So we're going to memoize, or basically kind of like cache. So what does that mean, Jonathan? What you can think of it means is that as I'm going through this my recursive tree, I'm just going to like record when I do work, right? Cool. I'm going down the right side of the tree. I do f of 2 for the first time. I'm like, okay, f of 2 is 2. So now I'm going to go ahead and put that on the side. F of 2 equals 2. Okay, cool. And then I do f of 3, that equals 3. Picture like I have like a slate or a notebook that I keep to the side, and I just write work I've already done to remember it later. Now when I get to this side, right, I'm not going to calculate f of 3. I'm going to go here, I'm going to go look over here, and I know the answer is 3. Okay, because I wrote it down for myself later. So I saved myself some work. And I'm going to do that every time I do a function call. I'm going to check to see, hey, do I already have it over here? Did I already do this work? If I already did this work, then there's no point in redoing it. Okay, I'm just going to go over here, grab the value, go on with my life. That'll be much faster. All right, let's try to implement this in Python and see what it looks like. All right, in case you're wondering, I actually did leave the program running since last time, and it's still going. So, needless to say, that is going to take way too much time in order for us to do anything. So we're just going to interrupt that, and let's try to figure out how can we deal with not repeating ourselves, not doing work that we've already done, because there's no point in doing that. All right, well, it's actually kind of simple. So there's a lot of different ways to do this in Python. There's actually libraries to help you memorize functions. What we're going to do is we're just going to have a variable. We're going to call it memo, and we're going to set it to none. All right, so what that basically means is that the first time we call this function, we haven't done any work, so there's nothing to record, right? And so we're not going to record stuff until we actually do some work. But eventually, this variable is going to be passed around between the function calls. You can think of the function calls kind of like office workers, and they're all sitting at their desk and they're just waiting for information to come back to them from the people below them, their subordinates. Their subordinates go do work, and when the subordinates are done doing their work, they hand their work to the superior, who takes his work and hands it to his superior. All right, that's kind of the way to think about this. Now, with this memo, what we're going to do is we're going to give them a clipboard and some paper and allow them to write down their work. So when they pass their work up to their superior, they're also going to pass this clipboard that has all the work that they've already done. So that way the superior doesn't have to recalculate anything that has not been calculated so far. How are we going to do that? So pretty simple. If memo is none, meaning it doesn't exist, we're going to make it a dictionary. All right, we're going to have key value pairs. The key is going to be the index, 0, 1, 2, 3, 4, 5, and the value will be the number at that index. So, for example, we'll have the key be 2 and the value be 2. We'll have the key be 3, have the value be 3. We'll have the key be 4 and the value be 5, etc., etc. All right, so first we need to check, hey, have I already done the work? Because if I have, I don't want to do any extra code. Just go look at the clipboard and tell me if, if the work's already done. So if num in memo, so if I already did the work, return memo of num. Great, awesome. Go look it up, okay? So, hey, we already figured out the number at index 4. Okay, great, just go give it to me. We're done. Other than that, if it's new work, we actually have to we can't just look at the clipboard. We have to actually, get out the calculator and do the work. Then we continue on with our function. We have the base case. This part is going to be the same, but here we're going to change some stuff. First, we're going to store our work in our key value pair system, right, our dictionary. And we're going to make certain that we pass it in. So I'm going to pass in the memo, all right, here. And then at the end, I'm going to return memo at num. All right. So that way we're going to call the function like we normally do, except this time we're passing in that key value pair, the dictionary. All right. And using that to check to see if we've already done the work. All right. So as you can see, the structure hasn't really changed, right? We still have a base case. We're still having the function call itself. We're still saying, go find me the number at the previous index and the number before that. All right. But we're also storing it in this, object, this dictionary memo, all right, and passing it between function calls so we can keep track of it. Let's see if that made anything any better. Much faster, eh? You could, I mean, the difference is night and day, right? Like before, I literally left it hanging from the previous part of the video just to see how long it would take, and it still didn't finish. When we do memoization, as you can see, we get this ridiculously large number. I don't even know what this number is. Don't get me wrong, I wouldn't even know what to call this, but we were able to calculate this huge number in like a blink of an eye. Now, there is one little wrinkle. This is true of Python, is that there's a very specific reason I didn't go over 999 or 1,000 in this case. So, for example, if I did like recursive fib of 10,000, this is going to run into problems. Okay, we're going to have maximum recursion depth exceeded because in Python, the recursion depth you can go for is 1,000. And that's just, you can set that yourself or try to get rid of the limit, but I would not recommend that. So just if you're experimenting with this and going for like really large numbers, I'm just going to warn you that if you go over 1,000, I believe if you even go over a little bit over 1,000, yeah, you get maximum recursion depth exceeded. I believe 1,000 is the upper limit of what you can get. So that's why I picked the 999 so that we would get right under it. Now, I know some of you in the back of the theater are saying, well, Jonathan, this is not the absolute optimized way to solve the Fibonacci for like a large number, right? Like even this, right? We're up to 999, but we still run into limits with Python. But for right now, as long as you kind of understand that recursion is breaking down a large problem into smaller problems until we reach the smallest form of the problem that we can solve without relying on other function calls, without relying on anybody else. Okay, we break the problem down to the smallest, simplest form and then work our way back up. All right, and then you also understand that we can make this whole process more efficient by saving our work as we go along. If you get those two things, then I will be extremely happy. And then when we get into dynamic programming, I can show you another way to solve Fibonacci, to generate the Fibonacci sequence that's even more efficient than this. All right, but again, recursion is one of those basic computer science fundamentals that you have to study. All right, and so again, I'm doing Fibonacci like everybody else, but it is a great example of how to do this. All right, so hopefully you enjoyed the video. As always, like and subscribe. Please visit Code Your Career, and I will see you guys next time.